For coming to my talk. I really appreciate it. I really didn't think this many people would come, but I'm really happy to see you all here. Anyways, my name's Jack, or Hulto, and I'm going to talk to you guys about how to get goofy with Linux kernel functions. There we go. A little bit about me. I've been doing rootkit stuff for about 2 years. I'm in my 3rd year here at RIT, and I do blue team, red team, and black team for RIT, CCDC, and RITSEC. 2 of my co-developers are Nicholas O'Brien in the back, thank you, Nick, and Rain, who can't be here today, and recently graduated. Anyways, what is a rootkit? Real basic. It hides things and allows you to maintain persistence and avoid detection. It's kind of the basic what a rootkit is. Originally, some of them were just like kits of shims. So you shim ls, netstat, etc. to hide your connection, hide your files. Whatever you're trying to hide, you're writing a shim for that binary. And then why write a rootkit? Obviously, persistence. For red teaming, we want to not get kicked out of their box. A lot of the red teaming we do is around like the competitions we host, like IRSEC, and also for our CCDC team, we red team them so that they can get practice, so that when they go to Northeast and Forrest is red teaming them, they know somewhat what to expect. So this project is born out of that and trying to help them get prepared. It's a little over-engineered for that, but we'll talk about that. So first off, how many of you know how Linux system calls work? Like a rough understanding. Okay, so what happens when you're writing a printf function is you have your printf, library call, you call that. And printf is going to make a system call to write to standard out. And so what it's doing is it starts an interrupt, and it specifies some values in the registers. The interrupt gets passed to the interrupt handler, which is up in the kernel. And it says, okay, this is an interrupt for a system call. I'm going to pass this along to the system call table, which then evaluates it and says, this is this system call, this is that system call. So if I want to do write, it's going to pass it along and say, oh, here is the source, the data I'm going to print, here's the output, so if we're doing standard out, that's that file, handle, etc. And after that, it does the stuff and returns back to user space, all from that one interrupt. And so what we do when we are writing a rootkit is we're catching the interaction with the system call table. So traditionally what happens is the rootkit overwrites the system call table. It's changing the actual address value. So we go find write, we overwrite it, and we have it point to our code in the kernel. That's usually some kind of a kernel module. So after that, you've hijacked code execution. You can do whatever you want, and then you can return data based on saving that original value. And this allows us to do things like hide files. So when they do a getDents call, you hook getDents and you hide the file. If they're doing netstat, you hide list processes, etc. Ideally, what we'd like to move toward, so that's a lot of the standard capabilities, and Goofkit can do a lot of that. We'd ideally like to do like port sharing, which is where even if a service is already running on a port, you also listen on the port as the kernel. That way, for like scored services during red teaming competitions, we can have a backdoor on any scored service that they have, which kind of sucks if you're blue team. So, oh well. Yeah. So let's get into it. What's actually happening? So again, getDents, file hiding. What we do is we have our magic string. We'll say like RIT red team, and any file that starts with RIT red team is going to be removed from the getDents entry. So we're actually making a call to getDents first, getting the actual directory entries, and then we look through it and say, oh, this one starts with RIT red team. Remove it. So anything that has RIT red team in it is going to get removed. Same thing with proc, basically. The only difference is we're checking for the process ID to hide processes, and we just verify that we're in /proc, so we're not hiding random files with the same number. Like if you hid process 1337, you don't want to hide all files that start with 1337. You really just want to hide that one. And so let's talk about Goofkit. So like I said, the standard rootkits are overwriting the system call table, and they're changing where the pointers are. This is kind of easy to detect. All you have to do is load a kernel module, enumerate the system calls, keep a list, and keep checking. And if the system call pointer ever changes, someone's done something, and you know that's bad. So what we're doing instead of that is instead of overwriting the actual pointers, we follow the pointer to the function, and we overwrite the actual function. So there's actually inline assembly that we're injecting into each system call that we hook, which hijacks control flow, and we save the original code so that we can jump back to it. The benefits, so this is called inline hooking. The benefit of this is that it's harder to detect, and then we couple it with trampolining so that instead of, like, sometimes you want to pause your rootkit, and to do that, traditionally what you've done is you've undone whatever writes you did to initiate the rootkit. So if you were overwriting the system call table, you wrote back your pointers. Or if you were doing inline hooking, you would rewrite the actual functions. Instead of doing that, we're doing trampolining. So we copy out the old code. We inject our hook. Our malicious function, if it needs to call the OG code, we'll call the copied out part and then jump to after our hook. And then just resumes execution. If we want to pause it, all we do is we skip over our malicious section and just let it keep going, because we've already saved the OG code. The benefit of doing these two things is it's harder to detect, and it is much less disk I/O whenever you need to pause it, which prevents an extremely niche race condition from happening. Which if it does happen, knocks their box offline, which isn't really fun for anyone. As Red Team, you're a part of the learning experience. You're not there to be a bully. You're there to help them learn. And it's extremely, extremely, extremely disappointing when your box just starts stopping every time you try and do something. And you're not going to learn a whole lot from that. You're just going to get sad and probably leave. So we're trying really hard to avoid that, which is why we're doing this. So are you guys tracking? Did I lose anyone about what's happening? If I lost you, it's okay. We're about to have some pictures, which I think will help describe this a little bit better. So here's a standard implementation. You have the system call table, and it hijacks the pointer to our evil write. Once there, after they call write, we get execution because the pointer's overwriting it. Now, here's what Goofkit does. Instead of hijacking the pointer, we leave it alone. And instead, we inject our malicious jump right there in the red box. And that'll jump to the kernel module that we've loaded. We do some execution bits. If we need to call the original code, we jump to the trampoline, which is the original code we saved. And then at the end of that, we return into evil function and then jump back to the original code, which is why it's a trampoline, because you bounce around a lot. So there are a few things in place that you have to overcome in order to actually do a rootkit. And the first one is you have to find the system call table. Every kernel after 2 has stopped exporting the actual Linux kernel table, the system call table. They used to just have it exported, so you could just call like system call table entry 2 or entry 3 and get write. But people were abusing it and writing rootkits for it. So they stopped doing that. They didn't do a very good job of protecting it though. Kernel space is pretty limited, so if you want to find it, you just have to search all of the kernel memory. You take a known value like sysclose, and you search for it in the kernel table. Once you find it, you know, this one's sysclose, I'll back up 3 entries, and that's the start of my system call table. And so that's what we're doing right here. This is what a lot of rootkits do. There's other ways to do it, but this is by and far the simplest and most common way to do it. So now that we've actually found our system call table, we're going to do an actual hook for it. So here's our malicious jump. and here's our OG code back here. We copy out the OG code, copy over our malicious jump, and then we build a trampoline from the OG code and a template of our jump so that we can, so we hook the function initially, we jump to our malicious code, which is out there. When we want to call the original function, we just have to call the function pointer for the trampoline, which will execute, jump back to the original system call, and complete execution there. Yep. So this is the inline hooking and trampolining. There's some protections like the CR0 bit, which prevents writing to the kernel, which is really great. The bypass for it is to turn it off. All you have to do is you write to the 16th bit in the CR0 register, set it to 1, you say allow execution. To disable it, you undo it. So that's all we're doing when we're writing to the actual kernel. And after that, this is what our code looks like after that runs. So we have our initial hook again, jump back, etc. So once you've hooked something, there's kind of two things you'll do. You're either going to do before you call the original function or after. You can just never call the original function too, but that's super suspicious. But that would be a way to break stuff. So like one thing you might do if you're doing like ioctal stuff, and you really need something to work, you can just hard code ioctal values, and usually if you just return 0, something will work. When you get into more complicated stuff, it stops working as well, but 0 is a good return value. But for this, I did a uname. So this was the first one I wrote just because it was super simple. All we're doing here is we are running the original function. We get the file struct, the struct UTS name from running the original code right here, which is this is our function pointer. We run it here. It creates this buff, and then we modify the sysname variable so that we change it from Linux to macOS. So if you're running Linux and you see macOS when you run uname, probably something wrong. And then the other side is we do the malicious stuff before we call the original function. So like with kill, so with our kill signal handler, this is how we tell it which processes to hide and whether to reveal itself or not. What we do here is we read the input, so we check the process ID and which signal is being sent, and then we see, okay, this is one of our control signals. We're going to handle it in a special way. If it's the process hide, it'll find the process, modify it, and then it'll go back to normal kill execution. If it's not one of our special signals, then we just let it go, and nobody notices. So, like I talked about, there's some protections involved. The system call table not being exported right here. This is how we get around that, by brute forcing. Do y'all know what ASLR is? So the kernel has its own version called KASLR, which took me by surprise because I was trying to load it into like Ubuntu 18.04, and everything was just getting scattered everywhere, and I didn't know what was happening. I started Googling, and I found out about KASLR, and I was like, oh, well, yeah, that checks out. But again, it's not too hard to turn off. All you have to do is set the no KASLR flag on boot, and then reboot the system. Not great for like advanced persistent threat actors, but for a college competition, that's fine. Module sig enforce. So this is probably the best way to prevent rootkits, is just to turn on signing enforcement. Super duper hard to fake a signed kernel module. It's not really like something you see happen. That's what this does, is it's just enforcing signed enforcement. It is turning on signing enforcement. So your kernel module needs to be signed before it can get loaded into the kernel. There's a few ways to prevent blue teams from doing this. One of the ways we do it is we just don't let them write to the file that would allow them to do this. It's super obvious because it'll say like permission denied, permission denied, permission denied, and you're like, I'm running as root, there's no SE Linux, permission denied. But they still can't do anything about it because what are they going to do? And then, yep, here's our CIR0 bit right here. Here you can see us disabling the write protection, and that's the little Wikipedia article talking about it. So recap, this is a super duper over-engineered solution to getting persistence on college students' boxes. We didn't have to do this. There's really no reason we should have done it this way. I thought it was cool, and so I did it, and that's about it. It was a really cool problem to solve. We did some like inline assembly, disassembly in the kernel to figure out where all of the instructions need to line up, and all of the trampolining. It's a super fun project, but again, not super applicable or super reasonable solution for college students. But it was fun to solve these problems. Yeah. Does anyone have questions or comments? Sure, what's up? VDSO, I don't know what that is. Oh, are you talking about like LD preload? Okay. I don't. Oh, okay. No, probably not, because I didn't know what that is. That's really cool. I haven't tried it. Be interesting to try out. I don't know enough about Fuse to tell you whether it should or should not have a problem, but it'd be an interesting thing to try out. Are you saying statically compiled to not allow boot flags, or? I have not. So actually the way to get around unsigned kernel modules that prevent you from writing is to boot into your BIOS, or to boot it to grub, and then modify it there, and you just have to do that every time you reboot, because you can't actually modify it while the system's running. So you have to boot into, you could live boot and modify this file there, or do it in the grub config. Does anyone else have questions? What's up? Yep, so this is for the Linux kernel specifically. It targets, oh, sorry, yep. So Jake asked, what kinds of kernels does this specifically target? We're targeting the Linux kernel. It's been tested on some versions of 4 and some versions of 3. It's on the GitHub if you want to check out exactly which versions are supported, but that's my project right now, is 1, figuring out which versions are supported, and then 2, adding more support, because there's a few things that still break. Anyone else? Okay. Yep. How long have you been working on this project? So this one I've been working on and off for about a year. I'm kind of excited to be somewhat done with it. I have a lot of other projects I want to move on to now. Yeah. Yeah, so should competitors expect to see this in upcoming events? Yeah, if I'm red teaming you, it might come up. Yep. Where do I see rootkits and stuff? Where? Ah. Mm-hmm. Okay, so the question was, where are rootkits going in the future? How do I think they're going to change? Where I want to take this is I want to move it away from a lot of the detection mechanisms that currently work. So Usually the way you detect a rootkit is through process hiding. So if they're hiding a process or the kernel module, you can detect that, because when you hide a process, you're usually hiding it from getDents, and so you just have to iterate through and check for known files in each process. And the process ID space is relatively small, so it's easy for a tool to brute force that. And if getDents doesn't show something, but the tool detects something by doing like fstat on /proc process ID / like file descriptor /1, and just checking if that exists, because it should exist. You'll run into a lot of problems where they'll just see, oh, yep, something's hidden, this is bad. Also, volatility supports has a tool where you can load in a volatility kernel module and just see like who's hiding on the kernel module list, because the way you hide yourself from the list of kernel modules is you unlink yourself from a linked list. And so they just iterate through and they check for gaps. All right, cool. Thank you all.